Ladies and gentlemen, here we are back at pre-calculus. They're all excited. It's so weird, right? But at least you know what's really weird is me talking to myself some days when I got to record lessons myself. That's really weird, right? And other teachers walk by and I'm talking to myself. And anyway, those of you that are listening to this right now, I'm talking to myself. Anyway, here's what it is. No, we have a class here. Um, we're moving forward today. We have a little bit of, we're doing the same thing we did the other day. We're looking at zeros, but this is called, they call it complex zeros. Some people call them imaginary numbers. We are going to be looking for all zeros, whether real or complex, and kind of what that means, what that looks like. Today is not going to be really anything different than you've seen. I'll be honest with you, it is going to be a little bit more messier than some of the things we've seen. I think it's kind of neat, but what I consider neat, maybe you don't consider neat too, but some of the math here. But this is not overly difficult. You can handle this. So again, next week we're going to come back, do some pieces and things. So here's what I have. So we're going to find all these zeros, what they are, real or non-real. Now, we've already talked about this, and maybe, again, on the quiz that you just took. Again, if something slices through my x-axis, that's a real zero. It just means that you have one of those. You have a multiplicity of one. If I find my object bounces off the x-axis, that means you actually have two of the exact same factors there. You actually have two zeros there. We have a multiplicity of two, but it's just in the same location. If it weaved, anybody have a weave on the quiz? Some of us should have weaves on the quiz. Some of us, not all of us. So some of you are worried right now, but some of you probably should have. But if it weaves, it means you have this. You have three of the same factors in that location. You have something to the third power. But these are all real zeros. This is where my polynomial crosses the x-axis, and I have these pieces and things. Now, here's what I want you to look at. I worked really hard drawing this. Look how hard I worked. This is a polynomial. This is the roller coaster. It's going up and down, doing its thing. It's a beautiful polynomial. My question, I have three questions for you. Could you tell me, by looking at this, based upon things we've talked about, what's the degree of this polynomial? Maybe I'd even back up a step and ask this question. This is an easier question. Odd or even? Is it an odd or even degree? Olivia says odd. Why odd, Olivia? Why? It's starting and ending opposite. Now, if I ask what's the leading coefficient, what would you say? Leading coefficient would be positive because it's ending up and starting. So I know it's odd. So my answer is going to be things like 5, 7, 9, 11, right? Anybody know what the answer is this? What's the degree of this polynomial? How do I know? For those of you at home, they're quiet right now. Okay, sorry. Oh, it's been a long time ago. One way if you want to find, is actually counting branches. Branches will tell you your degree. When I say count branches, how many times does it go up and down, essentially? Count some branches with me. Let's count. So, for instance, I have one branch up, 1, 2, little branch, 3, 4, 5, 6. This is 7, 8, 9. Is 9 odd? Could this have a degree of 9? This has a degree of 9. This is what this is supposed to have. But now as I look even closer at this, though, the last two questions for you is based upon these degree of 9, how many of these are real zeros? So when I say real zeros, when does it really cross the x-axis? Like right here, does this cross the x-axis? How is it a slice, a bounce, or a weave? What's the multiplicity? Like how many real zeros are there? It's a slice. So there's only one real zero. This is a real zero right here across the x-axis. But this is a what? A bounce. And again, what's that mean? It means you have how many zeros there? We got 2. So there's 2 zeros there. This is a slice. This is meant to be a slice. Sorry, I didn't draw very well, right? This is meant to be a slice. This is a slice, another slice. If you add these up, how many real zeros are there? There's 1 here, there's 2 there, there's 1 there, 1 there, 1 there, 1 there. There's a total of what? 7. There's 7 real zeros. This has 7 real zeros, which means if my degree is 9 and 7 of them are real, that means that there's 2 that are not real. There's 2 that are what they refer to as complex. These 2 numbers here have to add up to be my degree. And again, I know we're going to talk algebra of this in a moment and stuff, but graphically, real life, right? Graphs are real life and stuff with this. This is what it looks like. This is what imaginary numbers look like. Do you see where my complex zeros are actually at? I don't know if you ever learned how to find complex zeros or imaginary numbers, right? I know we define imaginary numbers. We're going to talk about this in a second. We define this to be the square root of -1 is I, but graphically, where do imaginary, what do they look like? Because they are represented in here. Samantha, you're nodding. Where are they? No, you were nodding before when I asked, but so I don't know. They're on the left side, right? If you close your eyes, imagine. No, sorry, don't do that, please. Anyway, we're teaching, and some students like, oh, I love imaginary numbers because I can just sleep through class and stuff because it's. No, sorry, that's a bad joke. Anyway, quit talking, Mr. Roy. They're on the left side. Here's where they're at. Do you see them? Samantha sees them. Do you see them? It's this. This is a real zero because it really crosses the x-axis. My graph went up. Guess what my graph did? It goes down, but what did it do? It didn't go down and cross the x-axis and come back up again. If it would have went down across the x-axis, guess how many times it would have to cross the x-axis? To get back to this point, it would have to cross twice. That would be 2 more real zeros. Even if it were to bounce off the x-axis, how many more real zeros is that? 2 more, right? Because my graph turns prematurely right here, there's actually 2 real zeros, or 2 imaginary zeros. That's where they lie right here. It's where my graph turns and actually physically does not cross the x-axis. Those are where imaginary numbers exist. Yes? Have you seen that before? Do you remember that? I don't know. Maybe you don't remember that stuff. But that's what imaginary zeros look like. But these 2, real and complex zeros, or imaginary ones, they have to add up to be my total degree all the time. So, with that being said, the other piece that we need to talk through, and then we'll do the math, and this is more the algebra side of things. Non-real zeros, complex zeros, imaginary numbers. These always come, and this is supposed to say right here, come in these things called conjugate pairs. This is a big word. Imaginary numbers always come in groups of 2. They always come in pairs. And the pairs always look like this. I might jot this down. You have something plus or minus something I is how they come. They refer to this first part. This is the real part. This is the complex part. And normally we always write them as the real plus or minus the complex part is how we write it. But notice it's always A plus and minus the imaginary part, BI, is how we write this. And that's the pair. That's what's called the conjugate pair. A conjugate is the same thing, but just a different sign in between them. So if I had a complex number of, let's say, 3 plus 4i, that's a complex number. I have this complex number, 3 plus 4i. What would be its conjugate pair? If I had 3 plus 4i, its conjugate pair would be 3 minus 4i. It's the exact same thing, just with a different sign in between there, right? I'm not changing the sign of the 3. It's just the number between there gets changed. If I had 2i, you're going to see this actually in a second, and this is, I think, one of our answers. 2i. What's its conjugate pair? Negative 2i. What's the real part here? If you just had 2i, what's the real part? If you have nothing there in front of it, what is actually there? Not 1, but this is actually like saying you have 0 plus 2, right? So what's its conjugate pair? Or, and again, do we have to have the zeros there? No, we can just write it as positive 2i, negative 2i. Those are conjugate pairs. They always come in pairs, though, all the time. The other piece that we need to remember is this is by definition algebra. This is what we can't do algebra, and algebraically, we cannot take a square root of a negative. And so as mathematicians, we define this to be this value, this number called I. I don't know who made this up, but that's what they decided to make up. So if there's anything, again, I need us to know this. The square root of negative 1 is always going to be I. That's algebraically how I get this imaginary piece. The other piece of this is if you were to square this, if I square this, what happens? I square the square root of negative 1, if I square this, I get negative 1. If I square I get I squared. This is also going to be a value that I need us to remember, is knowing that I squared is negative 1. Yay? So, two things I need to show you. Two things we need to do. Want to go easy, want to go hard? Where do we want to go first? Easy or hard? I should say easy or more challenging. To go more challenging to begin with? You up for this? We've actually done all this stuff already. So here's where we're going to go. Skip this. We'll go here. This is where it's going to be more challenging. There's two types of problems I need us to work out today, and we've done this already, just now with complex numbers. So stay awake, bear with me. I want you, they're going to ask us to build, again, a polynomial given these zeros, is what they're going to ask for. We did this the other day, actually Wednesday, I think, is on the assignment Wednesday. The only problem, though, is like Wednesday's assignment said this. Wednesday said your zeros are things like this: x equals 3, x equals negative 4, x equals negative 2. Do you remember how we built the polynomial? What do we do with each of these answers, these zeros? To build the polynomial, you had to do what? You wrote each of these as a, remember this? You wrote each of these as a factor. So if I said, what is 3 as a factor? You said it was x minus 3. If I said, what is negative 4 as a factor? You said that's x plus 4. And then again, just as an example, this is negative 2, that's x plus 2. And what do we do with each of these factors then to build my polynomial? We FOILed these things out. Yes, do you remember this? A little bit of work here, right? This is the same question. The only difference now is this is, as I read this, I want to make a polynomial that has a degree of 3. So I have a degree of 3. So I get all said and done, degree of 3. But these are my answers. Look at this carefully. I have 1 0 is 4. Another 0 is 2 minus I. What are we missing? How many zeros should I have if I want a degree of 3? 3. How many are they giving me? 2. Why? Because you know the third one. What is the third one that they don't tell us? Anytime, you got to know this. Anytime I have a conjugate or a complex number, I need to have a pair. What's its partner? What's its conjugate pair? If you have 2 minus I, I also have to have. So this is my third one, 2 plus I. These are my 3 factors. And guess what we're going to do now? The same thing we did on Wednesday. We're going to build a polynomial with these 3 answers. And it's going to be a thing of beauty here. So, how do we do this on Wednesday? If 4 is a 0, that's a 0. How do I write it as a factor? That's easy, Mr. Roy. That's easy. Here's where the fun part comes from. If I took, let's see which one I'll do first. I'll do this one. 2 minus I, that's another factor, right? Or that's another 0. How do I write this as a factor? Because it's complex. It's not just like 2, right? How do I write it as a factor? This is how you're going to do it. And I want you to know this, because this, again, it's not hard. It's kind of fun, actually. It always is this. So watch this carefully. You're always going to write x minus. Even here, what was this? This was this piece right here. This was what? It wasn't just x plus 4. It was x what? X minus. And what did I do? I just plugged in the 4. If this would have been a negative 4, then I would have wrote x minus, and then I would have plugged in a negative 4, which made it x plus 4. But I always write x minus. So what do I have? I have x minus, what's this 0? It's x minus, it's 2 minus I. Notice I put it in parentheses because it's x minus this quantity. So I'm going to put it in parentheses. That's important. But I write my factors always as x minus. X minus. So my last one, if this is my other one, again, how do I write this as a factor? It's going to be, say it out loud, x Oh, just say it. It's good. Otherwise you're going to forget it. Trust me, I know. X minus, plug in my factor. And if I have a complex number like this, I put it in parentheses because it's minus that whole quantity. And guess what we're going to do with this now? We're going to FOIL this thing out, and it's going to be a thing of beauty. So, does that make sense, though? Always, all I'm doing is just plugging in these pieces and writing an X minus, and then now I just need to FOIL it out. You ready to do this? You have room on your paper? This is going to get big. You ready for this? I didn't say anything. No. I personally, if I'm doing this is what I would do. I would do the complex ones together. You can only multiply two things together. I would do these two together because together they're actually going to make something really nice. Before we even multiply them, though, me personally, I used to teach this differently. I think I would do this. I would take this negative and distribute it first. The same way here, I take this negative and distribute it first. So this is still, I have this X minus 4. I'll come back to that later. That'll be the last thing we deal with. But over here, we really have X minus 2, but then plus I. If I distribute that negative, and on the other one we have X minus 2 minus I, if I distribute the negative there. But I would distribute the negative through the parentheses first. I think it's a smidge easier doing it that way. Now, how do I multiply these two pieces together? I'm just going to have to, one by one, go through and multiply them through. And as you do this, it's going to look bad, but then it's going to look really nice. So go with me. What is, if I go X times X? What is X times X? That one's easy. That's just X squared. So this is just going to be a big mess here. X times negative 2. Negative 2X. X times negative I. Negative IX. Negative XI. However you want to write it. Negative, then I go to negative 2. Negative 2 times X. So I take that one through. Negative 2 times X is negative 2X. Negative 2 times negative 2. 4. Negative 2 times negative I. So negative and a negative will make it a positive 2I, so we get positive 2I. And then I go my last term. My last term is I. What if I take I times X, positive XI. I times negative 2, negative 2I. Almost done, running out of room. I times I. No, actually, I times negative I. I times negative I. Negative I squared. This whole thing turns into this huge mess. Does that look nice? No. But if you look really closely, though, this thing cleans up really nicely. What cleans up as I look at this? So as you start going through this, though, what things can I combine together? I have if I look at the very start, do I have any more X squareds? So I have an X squared there. Bring it down. I have a negative 2X. I have another negative 2X. So together that's going to make a negative 4X. Now if you look close, though, I have negative XI. Negative XI. Look. Do you see it? What else do you have? You have a positive XI. Guess what? They go away. Cancel out. If you look even closer over here, I have a positive 2I. You also have a negative 2I. These are going to go away. The only thing that's still standing now that we haven't used yet is we have a plus 4. The other thing that's still over here that's kind of messy is this, is we have negative I squared. But we just wrote down, I don't know if you remember, we wrote down, we said negative, or no, we actually said I squared was what? I squared is negative 1. So if you have negative I squared, that's like saying negative of negative 1, which is really what number? This is going to be a plus 1. So you actually have number-wise yet, you have 4 plus 1. What's 4 plus 1? 5. At the end of the day, if you do this right, even though these two complex numbers as factors, it's going to look like that, but they simplify into a quadratic. Are there any i's in this? No. If you were to use the quadratic formula, guess what my answers are going to be? If I do the quadratic formula, you're going to get 2 plus and minus I is what you're going to get. If you want to do it, we can do it. But that's what those two factors come out to be. What's my last step, though? The last step's the easy step now because you've done all the hard work now. Maybe. Last step's what? What's the last step? Can you multiply these two together? Multiply these two together. Again, I know it's a little bit of work, but can I multiply these pieces together? So today on the assignment, this is going to take a little more time. I don't know if this, does that make sense what we're doing though? Getting to this quadratic, that's sometimes the hard part. But now my last step, can I multiply these together? Yeah, I get x cubed. I get a negative 4x squared. I get a plus 5x. If I take the negative 4 through, I get a negative 4x squared. I get a positive 16x. I'm going to get a negative 20. And at the end of the day, when I collect like terms, when the dust settles, what's my polynomial? What do I end up with? I end up with a x cubed negative 8x squared, sorry. Then I have a 21x's minus 20. I want you to be able to take answers. Those were, I had three roots. Can I make a polynomial out of them? You feel like we could do that? But setting it up, it's always x minus, and if you have complex numbers, x minus that complex number. And a little bit of work. This is going to be a little bit of the pain. So if there's going to be anything that's going to take a little space and paper, a little work, a little elbow grease, it's going to be this. But notice, do I have a degree of 3? Polynomial degree of 3? Yeah, this is it. You can build the polynomial. You should see their faces in class. They're all so excited. You're like, oh my gosh. They're like, look at them. Like, 5 of us are doing this. Oh, I'm trying here, people. I think I'm going to go back to original Mr. Royak here. All right, class. Today we're going to instead, let's just, can we do this now instead too? Don't rush now. Don't get excited. Just take your time now. At least some of you are smiling now. Good. I can't do that. I can't keep going there. But this is some good, look at, this is some good math here though. This is like, look at the math you're doing here, right? Your 3rd grade self would be so proud of you looking at this math, right? If they could look at the future and look at your notebook right now, boom, look at that. That's a mess. Eyes? You wouldn't even know what an eye is in 3rd grade, right? Anyway. Here's the other half of today. The other half of today. This is the same thing as yesterday. I want you to do the same thing we did yesterday. I have a polynomial. Polynomial degree is 3. How many real zeros could I give? I could have 3 real zeros, right? What's my other option? My other option is I could have at least, because the other option is if I could have 3 real, or if they're already imaginary, they have to come in pairs of 2. So I take away maybe those 2. I'm guaranteed at least 1 real zero, right? This has at least 1 real zero. What did we do yesterday to find my real zeros? We graphed it. So if you have a graphing device, you have one, do it, right? I know you can watch me do it. So that's fun. You try graphing this. Take a moment, graph this. So if I have x cubed plus 2x squared plus 4x plus 8, take your graphing device, see if you can graph it. Those of us watching at home, trying to fall asleep, no, I don't know. Can I put this on here? Can I do both? I don't know if I can do both here. No. Yeah, almost. Maybe I can do both. Oh, I can't. I lost it. You see both. Again, where do you go? You go y equals. I'm going to clear this out right now, but just type it in. I have x raised to the 3rd power. Bring my cursor down. Plus 2x squared plus 4x plus 8. Hit graph. Whoa, this is what my picture gets. Is that what your picture looks like? Give me a moment. If you look at this, though, how many times does it cross the x-axis? Your picture or my picture? It crosses only once. You have 1 real zero. What's that mean about the other 2? They're probably going to be imaginary, right? So what did we do yesterday? What is my nice real zero here? What's it look like? -2. So I go to, again, the proof in the pudding that I want to see is this is, I don't want you to say, well, x equals -2, Mr. Roy. The proof in the pudding is this is, what's true about -2? I should be able to do what with it? I should be able to divide it out. So if I divide it out, synthetic division is my choice of dividing options. If I divide this out, I'm looking for a remainder of 0, bless you. If I bring down the 1, multiply -2, add, I get 0. Multiply, I get 0. Add, I get 4. Multiply, I get -8. Do I have a remainder of 0? The answer is yes. So is -2 a 0? Yeah. Now, what's that mean algebraically? It means what, though? It means my board doesn't work. If I take it out, what's left over? So if -2, I'll write it as x plus 2, but what's left over is x squared just plus 4. Now this itself, again, can I factor this quadratic? It's a quadratic. Can I factor it? This is a sum of squares. Can I factor a sum of squares? No, they don't factor at all. My only option, or really two options, I could quadratic formula it. Quadratic formula will always work. The only thing to be aware of, what's the b value? 0. The other option, do you see the other option solving? If I want to find zeros, that's my goal, finding zeros. The other option, because this is like this, you could just take this and set it equal to 0. I don't know if you did. I think this is easier than the quadratic formula. Can I solve for x here? Do what? Subtract 4. How do I unsquare something? Square root. Just know when I take the square root, though, I get plus and minus. This is what I'm going to get. I'm going to get plus or minus the square root of -4. Again, what's the issue with that? Can I have a square root that's negative? No, but we just said, again, it's going to be imaginary. What's our definition for an imaginary number? It's if you have a negative inside my square root. So this is actually the same thing as the square root of -1 times the square root of 4. But what is the square root of -1? I. What's the square root of 4? 2. My answer here is going to be what? What are my zeros with this? You're going to get x equals plus or minus 2i. And so my zeros, because that's what they want to know, what are my zeros? My zeros are going to be x equals -2, right? We said that before, x equals -2. But my other two come in a pair, conjugate pairs, and they're imaginary. They're plus and minus 2i. So I have 3 zeros here. 2 are imaginary, 1's real. You saw it on the graph. It only sliced through one time. But that's the other half. This is really the same thing as yesterday, except for you might find this not to be real answers, but imaginary. Negative, but not a perfect square. Like, what do you mean? What if I had, so here's the question. What if I had like x squared plus 5, right? That's what Olivia's asking, right? Kind of, right? If I set this equal to 0, I could do the same thing here. -5 equals x squared. Take the square root. Here's what I'm going to end up getting here. I'm going to get x equals plus or minus. Because I have a negative, I'll pull out that I. But then here, I just have to leave it as the square root of 5. So it's going to look like, you normally write the I first. Is that how you guys did in Algebra 2, the I first? Different math teachers do it differently. The I and then times the square root of 5. But that's how I'd rather write it. Leave it like that. And again, if this would break it down, but square root of 5 doesn't break down, so I'd leave it like that. Is that your question? Yeah. Do you think you can do these two types of things? This is going to be what we did a moment ago. Building these, that's going to be a little more work, right? A little more work. This is going to be a lot like what we did yesterday, which hopefully wasn't horrible to do. Do you want to see more? Mr. Roy, you got more? Gabe? No, Gabe. This is actually a fun question, but we'll save it for another day. But can we try? We actually, because we didn't present, we didn't have 5 people presenting like second hour, and because my computer did not freeze up and have to be restarted, and because I had the microphone ready to go, we have more time here. I don't know if we know. Do we feel like we know what's going on though? Now here's actually before you write though. I told second hour this. I told them if they did 39 through 43, again, all of them, that'd probably be enough practice there. If you want to do 37, 38s, they're kind of mid questions. They're not that. These first 4 questions are going to be making the polynomial. Be honest with you, that's if you want to get anything done right now, I try this right now. Make sure you can set this up, because if there's going to be questions on the homework, it's probably going to come from these first 4 questions of, can I build the polynomial? How do I multiply these things out? Did I write it right? Did I multiply them out right? The last 6 questions, 7 questions, we're looking at, just for you guys, we're looking at, I think you're going to break it apart. So if you need a graphing device, again, Desmos works. If you don't have a graphing calculator, some of us that don't have graphing calculators, is there any hope that we can get one? Like an early Christmas gift and say, Mom, Dad, Christmas this year, can I get a graphing calculator? Or I know my birthday is not until April, whatever, can I get a graphing calculator? They're still cheaper probably right now from the back to school sales than they probably ever will be the rest of the year, whatever it's worth and stuff. I know these school ones are nice because they're colored. You don't need a colored one. You can just get a black and white one. If you have an 83, TI 83, those also would work. There's some things in calculus might not be able to do on some of the 83s, but I don't know. I'd encourage you, if you can get a graphing calculator, if you're going to do more math the rest of this year, I would want one to do some pieces and things. All right, those of us at home, thanks for listening. I know it's super exciting. If you haven't fallen asleep yet, enjoy your rest. We'll see you tomorrow. See you the next day.